So we're going to do two things this afternoon. First, we're going to talk about qubit measurement, and then I'd like to talk a little bit about error correction and an error correction experiment we did. I think you're learning that from other lectures, but I'd like to kind of present a simple way to think about that and kind of discuss what we're doing there. Okay, how do we measure our qubits? Remember I said that, if the qubit is a nonlinear oscillator, so you should be able to measure the state of the qubit by measuring its oscillation frequency. If it's in the ground state or if it's an excited state, it has a different oscillation frequency, okay, and you should be able to directly measure that. So if I take a qubit transmon system of a junction and a capacitor, okay, and we might want to measure its resonant frequency, then what I'm going to do is I'm going to take a coupling capacitor and then to a microwave line and an amplifier, and we can put in photons here and scatter them off of the qubit, amplify them here. As we did, I was talking about how we were measuring LC resonators. We can measure the resonant frequency and parameters of that. We should be able to measure it this way. Okay, in fact, people have done experiments like this, but there's a problem in doing it this way. Can people see what the problem is? Okay, it's maybe a little subtle, is that if we want to scatter this strongly off of this to get a good signal here, it means the damping from this 50 ohm line is going to damp our qubit. So we're going to get a measurement, but when we're not measuring, this measurement circuit is going to damp the qubit and cause the qubit to be bad. Remember, there's a 50 ohm resistor, coupling capacitor. If this is strongly coupled, to be able to see this well, it's going to get messed up. Okay? So there's a very interesting trick to get around this, which of course was invented by the Yale group as they worked on making dispersive measurement. And the basic idea, you look at that circuit and you just make it a little bit more complicated, is that you have your qubit and you connect it to another resonator, and then you measure this resonator in the way that I talked over here. And what happens is you detune this by about 1 gigahertz from this. And this detuning means that through this coupling right here, this resonance frequency will pull this frequency due to the coupling between here. And then so that this frequency will change depending on what this frequency is. And then you're just going to directly pull the change in frequency through that circuit. So you kind of do it in 2 steps. And what happens is this being detuned from this to this causes this not to be damped by looking out into this circuit. And yet this changes its frequency enough from its dispersion interaction that you can actually measure what's going on there and measure the qubit state. So you're kind of doing this in 2 steps. Any questions on that? I mean, it's really a simple idea here, what you're doing. But, we have to work through the dispersion physics. Okay. So the basic physics here is that the coupling, off-resonant coupling of this between the ground state and 0 state changes this frequency. And that way, when you put a signal through here and reflect it off of here, whether this is one frequency due to the ground state or another frequency to another ground state, this will shift here. And what happens is, if we're in the ground state of this qubit, the signal coming out of here will have a certain phase This is the real and imaginary part of this output signal in the rotating frame I was talking about. It'll have a certain phase. And if this is in the excited state, because this frequency different, the reflection coming off of here will be at a different phase, because it's a different frequency and it reflects differently. And when you do that, you're going to get an entangle. Let's say if it's an excited plus ground state of the qubit, 0 plus 1, you're going to have some entanglement of the 0 plus 1 into these two coherent states. But then as this coherent state gets read out, this state wants to collapse into one of these two states, and then it'll do so 50% collapsing of the time into here and 50% of the time collapsing into here, and then you can read out what state you were at. Because this state, a coherent state being both here and here, very much separated by a long distance, is a kind of unstable quantum state, and a small amount of dissipation from the system here will cause that to lose its coherence, and then it'll collapse, and then you'll get the measurement. Okay? So that's the basic idea. Questions on this? Okay, so let's talk about how this works in detail, starting with the dispersive physics of resonators. And we started that discussion before. We were talking about, as we changed the frequency between resonators, we have a avoided level crossing. In this region here, we were talking about making the gates where the two qubits interact with each other. But when one qubit, the qubit frequency is very different than the resonator frequency, say about a gigahertz, you then have a very small dispersive shift. And in the dispersive shift, where this omega frequency difference is much bigger than the coupling, G is typically 100 megahertz, we're detuning it by a gigahertz or so. So this condition is true. When you work that out, the frequency shifts. The qubit frequency shifted by the resonator, and the resonator streaking by the qubit is given by this. It's basically G squared over delta, the frequency difference. This is both the classical calculation and the quantum calculation. Okay? So that's it. And thus, if the resonator is shifted by G squared over delta, you can observe that. Now, the way things work with a qubit and a resonator is that the qubit has a frequency that corresponds to G, let's say 6 gigahertz when it's in the ground state. But when it's in an excited state, because of the nonlinearity, it's dropped from 6 to about 5.8. It's changed by a distance eta. Okay? And then this qubit is connected to a resonator, which has a detuning delta about a gigahertz. And because of the interaction between here with about 100 megahertz coupling between G, the resonator states will shift upward. It gets level repulsed. For the ground state, it's just G squared over delta, because the frequency difference is from here to here. But for excited state, it's G squared over delta plus eta, because this is a little bit different frequency here. So if you want to know what the frequency shift of the resonator between these two states, you just do the simple math here, and that's basically proportional to the nonlinearity times G squared over delta squared. Okay? And that's the signal you're looking for. The resonator frequency will change by this amount whether it's in the ground state or the excited state. And that's what we're going to measure. Okay? Now this is very simple classical calculation so far, just to show you what the physics is. Typically when you look at it, you look at a much more complicated level diagram. That's what I want to do next, and show you how that very complicated level diagram gets you to this idea. But that's the physics. Okay? Very, very straightforward physics. Okay. So let's go through the quantum mechanics. In the resonator, we have a, let's say 6 gigahertz resonator, equally spaced energy levels by 6 gigahertz. Let's say the qubit is parked at 5 gigahertz. So this is 5 gigahertz, and from the next excited state is 4.8. The next one is 4.6 because we have a nonlinear at 2.2, and we're a 0.2, and then these are detuned by about a gigahertz. Okay? So that's the setup, and now we have to take the tensor product of this to see what happens because these are interacting. So we have a level diagram of all the possible combinations of the photon states here from 0 to big, and the qubit in the ground excited, second excited, etc. So this has the full state of the resonator qubit with all the frequencies put in there. Now this is with the two isolated systems. Okay, now we're going to couple them together, and that's going to be with a G, okay, which couples which swaps a photon from the qubit to the resonator. So there's manifolds of constant excitation between 1 and G and 0 and E, where this will go to 0, you'll lose a photon, this will gain an excitation, ground excited. So these two are going to be coupled by G. Similarly, this is going to be coupled here, where you lose the excitation gain here, and also these two will be coupled. So given the coupling and using the rotating wave approximation, where we're conserving excitation number, we have bands across here, and I'm going to write them in terms of that. And because there's, in the creation operators, you have square root of n factors. Most of these are G, but there's actually increased coupling between these by these root n factors, which you typically see from the creation operation operators when you connect the states. And things are pretty much a harmonic oscillator, so that's good. So there are bands here of constant excitation number. Okay? And that's with coupling. And of course, when you get coupling, these two are going to couple together, and you're going to get repulsion of the states, for example. Okay. Questions so far? Okay, so that's how you set up the quantum mechanics problem within the rotating wave approximation. And we're going to have the different bands. I'll call them band 0, band 1, up to band 4. Okay, and if you want to solve this problem quantum mechanically, it's nice because now you don't have to look at the full state. You just have to solve the problem across the individual bands. So that's easier to do. And you can solve this trivially. These you might have to use numerically, but it's just not hard to solve that. Okay? So what we want to know in dispersive readout is what is the frequency of the resonator. And the frequency of the resonator is basically what is the energy of the resonator qubit, the resonator system, as you change the qubit number. That's the spacing h bar omega. Okay? And in a discrete limit right here, it's just the energy of this state of n photons minus the energy with n minus 1. So it's just these are the states and dashed lines of what happens when you interact. I just want to know the energy difference between here and here. Now what we can do, and this is the standard approximation that's made when you look at simple understanding of what's going on here, is we're going to say, let's just consider two states here. Let's ignore all those other states over here. Because if you have two states, you can solve that easily quantum mechanically, right? You just have a two-state system. You have a splitting between the two states. That's a delta over 2. Positive and negative, so you're in control vector in energy, and this is delta over 2. And you have a transverse coupling here that's root ng going in this direction, so that the energy change here is just, the energy is just given by this, right? Remember, you just add these two vectors in quadrature to get the total length. And then if I want to compute what dE dN is, I just do that, and you get this formula here. Okay? So when you have a band N, you have the bare, you have the coupling. These get split apart in the normal two-state way. You compute that. Okay, I hope you can kind of follow what the mathematics is there. Very straightforward. Okay, so for the two-state system, you see that if you're in the ground state of the qubit, you have a plus of this here. This moves up, and if you're excited state here, all these things move down, given here. And then the total dispersive shift would be twice the individual one. And here's just the plot of that. Okay, it's the dispersive shift. So the resonator frequency changes. If you're in the ground state, the resonator frequency changes by g squared over delta, according to this line right here. And if you're in excited state, it's the negative value right here. And then I've plotted this as the number of photons in the resonator. Okay, and typically what people do is they talk about what happens at low photon number, and this number is just g squared over delta. Okay, and g squared over delta. Note that as you increase the photon numbers and you try probing the system with more and more photons, okay, the dispersion goes down a little bit. So the frequency change is going to be a little bit less. You're going to see a little bit less opening of those two coherent states. But of course, if you drive it stronger, you're going to get a bigger signal, so it's going to be easier to do that. And the kind of characteristic energy at which this rolls over is when something called n crit, when delta is the number of photons of n over delta over 2g squared. And this particular simulation, that's about 25 photons in the resonator. You start losing the dispersive shift. Okay? There's the simple math. Everyone okay with that? Now what happens is that was the two-state approximation where these guys are repelling each other, but you want to include all these other states here. And this state is repelling this state, so because of that, this state since it's getting repelled by this state, this is not going to be repelled quite so much here. So you have to do the full thing. And one can solve this numerically. This is not a very hard problem to solve numerically. And when you do that, you get the results right here. So the ground states stay the same. Okay, because it was only that simple band. But when you go to the excited state and other states here, instead of the dispersive shift being way up here, it's way smaller down here. Okay, and now the dispersive shift being from here to here is smaller. And this value here is about 2 times eta g squared over delta. Okay, so there's an extra factor of, this should be a delta squared here, excuse me. So this is what you see over here. And if you remember that it's about 2 times ng squared over delta here, at high powers it's eta g squared over delta squared. And if you remember, that's what I computed classically a few minutes ago. Okay, so that was the initial guess that we had. And actually, the initial guess is much better approximation what's going on than the two-state approximation full quantum. That's actually, it doesn't have a factor that's important here. And you don't have to do that. And again, this changes a little bit when you get to n crit about 25. Okay. Were we okay with that? Okay, so this tells you what you need to do. So typically we detune by about 1 gigahertz. We couple the qubit to the resonator at about 0.1 gigahertz. Eta is about 0.2 gigahertz. And this frequency shift here is a few megahertz, maybe 5 megahertz or so. Excuse me?
What was n critical again?
So n critical, this is very important, in fact. N critical is basically where this curve here starts to change because you can't take the n equals 0 limit. It's where you can no longer take the n equals 0 limit, but you have to take the full n. And what happens when you get up to n crit is that these g's are strong enough that you're starting to excite all these states. When n is less than n crit, you're mostly here, and you're mostly in these states right here, and you have very little excitation in these higher states. But when n gets bigger than n crit, you start exciting a bunch of these states, because these guys, this root ng, starts getting to be the same magnitude as the detuning. Yes. So n crit is when your coupling is getting equal to detuning, and then you kind of have to do the full calculation. Okay? That's what's going on. Now, if people in the field, you're going to be confused if you've read experimental papers on n crit. So there's a little bit of confusion here I'll have to explain. Okay, but that's the basic theory. So what happens here is you have, these are the dispersion curves, how much the frequency changes. And you see you put in maybe 50 photons in the resonator. And of course, when you excite it with a mean number of 50 photons, there's a Poissonian distribution around that. So you're actually exciting that from 50 plus or minus 7. But you see over that 50 or plus or minus 7, the dispersion is more or less constant, so that you can more or less think of it, this is as a coherent state dispersed by that. But because the angle dispersion in this direction of the resonator is a little bit different from this photon number to this photon number, you don't exactly have a coherent state anymore. That gets squeezed a little bit. And so it's slightly different than a coherent state. But this doesn't really matter too much, but that's what's going on. And the same thing with the excited state, but here you see the excited state is very flat. So excited state up here would be pretty much looking like a coherent state. But then again, the whole thing go ahead and works properly. Okay, so you then measure the phase shift. So here's a picture of one of our old devices where we had a qubit here, which could be either in the 0 state or the 1 state. There are two different frequencies. When it's in the two different frequencies, this frequency of this resonant circuit right here is going to change by a few megahertz. Okay? And then we measure that by putting in a microwave pulse into here, which interacts with that and reflects off of that. And whether this is in one frequency or the other will cause a phase shift in the reflection signal. And then this goes out here to a quantum limited preamplifier, and then we look at the phase of the signal here, and we can tell what the state of the signal is. Okay? So questions on operationally what we do? So here's the photon numbers. We drive it hard to ring it up, and then keep it constant for maybe 100 nanoseconds, and then we turn it off and it decays, and then we can use the qubit after a few hundred nanoseconds. We looked at this reflected signal here and measure its amplitude and phase, which we write as a real and imaginary part of the reflected signal. And if it's in the 0 state, the points come up here, and if the 1 state, the points come down here. And each of these data dots here is one experiment. So we will have done this a few thousand times. And you see it's a nicely separated signal where we get two different responses from the 0 and 1 because of the phase shift, the frequency shift of the resonator gives us a phase shift of this measurement signal. Okay? And what we can do is draw a line right here and say how much, to separate these, how much are you this way and how much are you this way. So the blue lines gets histogrammed into a nice Gaussian over here. The reds get separated, a nice Gaussian over here. There's some overlap, so we are going to misidentify some points. Red points, so what should be over here, and a few blue points here over here. So there's going to be small errors. And if you plot what that, you draw a line here and plot what those errors are versus this pulse integration time, which is the distance from here to here, okay? Then at small pulse integration time, you have pretty high errors. And then for this qubit here, the errors go down to about here 10 to minus 2, maybe a little bit below 10 to minus 2 once we integrate to 140 nanoseconds. And the other qubit, which is our slower qubit, you want to integrate a little bit more till you get the small error rates. Okay? And, you know, so, and you can get errors in around the 1% level looking at this way. What's happening here, this is staying constant here, it's not getting better as you integrate longer, is that the qubit is actually relaxing during the measurement time. So this is 100 nanoseconds or so. Let's say it's a 10 microsecond qubit. It's about, that's 1% of the coherence time. You expect in that measurement about 1% of the time it'll relax, and thus you're leveling out to that kind of number. Okay. Okay with that? That's operationally what's going on. In this particular circuit, what we actually did is had two qubits, and we have these resonances, resonator frequency here. They're different lengths. So one's a higher frequency, let's say 6, and the other was a lower frequency, and this is a higher frequency, maybe think around 6.2. And what you can do is you can drive this with the two different frequencies, and this frequency only resonates and interacts with this. This frequency only resonates and interacts with that. And then you have an FPGA that specs out, looks at those two different frequencies, and you get an amplitude and phase from the two different frequencies, and you understand that. So if you started in state 0, 0, and you look at your readout signal on Q2 and the readout signal at Q1, you get a blob here that corresponds to 0, 0. You then put it in 0, 1. This state here is the same readout signal, but the other qubit had this readout signal here, 1, 0, 1, 1, and I kind of mirror these four over here, and you see a good separation and low crosstalk. It basically shows you can frequency multiplex the measurement of these two signals, and everything works out okay. It interacts with them separately. Yes?
So can you measure the qubits and then act on, like, keep doing quantum?
Yes, yes, it's possible to do that because the measurement times are 100 nanoseconds or so. And in fact, I'll show you an experiment where we did that. But yeah, in fact, you want to do that. I'm going to say, you know, we want errors a little bit below 1%, so we have to do this better. And we want a little bit shorter measurement time, so some work needs to be done here. And of course, those trade off against each other. But things work well enough that, you know, you can imagine doing things well. But we have to work on it some more. Now, one of the problems is that although here I told you how doing the measurement, you know, quickly also affected the coherence of the qubit. Okay, there's a trade-off between how fast we can measure and how fast we can measure, which is this kappa parameter, which has to do with the coupling capacitor there, and what kind of T1 you get, because your measurement circuit actually, even though it's off resonant, damps the circuit a little bit. And it turns out when you work that out for the circuit I talked to you about, that's delta over G, which is basically N crit. And this gives you a pretty severe limit on making the measurement faster while not screwing up the qubit. And it turns out, thinking about that circuit and what we did here, there's a very simple way to do that, to fix that, is besides having the qubit and connecting to a resonator, you connect to a second resonator before you read it out to act as a filter. So the one resonator is kind of a one-pole filter to filter out the measurement from the qubit separately from damping of it, and then we just put in a second filter to do it even better. So this second filter, in fact, in this structure here, is this line right here, and forms a second low Q resonance. And in fact, when we look at the transmission of power through here, we can see this general response here in the green line having to do with this filter right here. And this is, of course, filter is set up at the resonators so that we can measure them very effectively. But then by the time we get to the qubit frequency about a gigahertz away, that filter is isolating the qubits from the measurement circuits further, and then the qubits don't get degraded. So you get about an extra factor of 100 better performance by putting in a second filter that further isolates the qubits. So the whole point of this filter, this resonator, dispersive readout, the whole point of that is to act as a filter so that at the qubit frequency, you separate out the damping from the qubit frequency from the measurement frequency. And then the measurement doesn't affect the qubit operation so well. Yes?
So how many qubits can you measure simultaneously, and what's the limiting factor?
Yeah, so the 9-qubit device I'll talk about, recently we did 9. And 5 of them were coupled strongly and 4 were coupled weakly. Right now we're designing around 6. So it's not a huge number, but you can't do a huge number because you have to read them out fast. So you have to have a relatively fast bandwidth, and that just gives you the frequency crowding. But since measurement is complicated, that factor is really useful. It's good. But it can't be 100, for example. I don't see how that would work. Yes, there was a question here.
Yeah, so it seems like from what I understand, filters exist to decouple the resonators with the qubits.
Right.
At least the second filter line adds that. Why is it a low Q filter? Why not use a higher Q filter to get more isolation?
So let's see. So we could do a higher Q filter here, and then we want to make sure, yeah, a higher Q filter would work, but we want to make sure that if we make that too high, then we're going to slow down the readout of photons from the resonator, from these resonant modes. So we don't want to slow down that too much. But it turns out this kind of Q, it could be designed better, but this is just very safe. It's not too hard to do that. But one could optimize that some more. Yes? Yeah. So right now we're using a Josephson parametric amplifier that has a relatively wide bandwidth, which is actually kind of hard to make, but we were able to figure out how to do that. We're also using the TUPA amplifiers, which have even a bigger bandwidth. Of course, there's a whole long discussion on doing that. But for frequency multiplexing, you want to have 300, 400, 500 megahertz of bandwidth. And that means that the typical Josephson parametric amplifiers, which has maybe 5 or 10 or 20 megahertz of bandwidth, really not good enough. So you have to build this special thing there, which is something we developed for this experiment. Okay. Okay, so that's all I had to say on measurement. I'm now going to talk about the experiment on doing error correction. And I'm skipping a bunch of slides because I've been going slow, which is good. And then let's go ahead and start talking about error correction and error correction experiment that we did. The basic problem, of course, is that qubits, physical qubits, have gate errors around the 1% and maybe 10 to the minus 3, maybe 10 to the minus 4 if we start really building very good systems. These are analog devices, so unless you get the topological qubits working really well and solve all of those problems, being an analog system, you're not going to get perfect qubits, perfect qubit operations. We're thinking about eventually building very complicated algorithms that maybe have the size scale of a classical algorithms that we can run about classically, that has maybe 10 to the 12 or 10 to the 18 steps in it. Okay, maybe 10 to the 6, 10 to the 9 on the initial ones, but a lot of steps. So we're going to want error rates that are 10 to the minus 9, 10 to the minus 12, 10 to the minus 15, 10 to the minus 20. We have many orders of magnitude to make up with error correction. Okay, so that's what we need to do. So what I want to talk about is a long-term plan on how we're going to make up many orders of magnitude. 10, 15 orders of magnitude. Now, I want to differentiate the discussion here with typical discussions you'll hear on error correction when you go to conferences and whatever. And what's happening right now is there's lots of different ideas for error correction, and experimentally, we haven't really gone very far for error correction. So if we do an experiment where we improve the error rate of a qubit by 20, 30%, maybe a factor of 2, that's a big celebration, Nature article, get invited to it, that's really great. Okay, so we've improved it by a factor of 2. I want to go, 10 to the 15. So if I think about this as something we celebrate, I'm giving you a story about how we go to the moon, okay? In distance. It's that much more, okay? And although the basic theory behind what we're talking about this is the same, you might expect that the hardware and the thinking behind how to do this and how to go to the moon is going to be a little bit different. So a lot of times I see what now people are thinking about things, and they're basically inventing bottle rockets, which is great. You do a rocket. We need to invent the Saturn V to get us to the moon. And the Saturn V engine is a little bit different and complicated than a bottle rocket engine. Okay? So this is all nice. We have to do this, but I want to give you a story right now on how we're going to build the Saturn V, how we're going to get to the moon, how we're going to do that, how we're going to get many orders of magnitude. And in fact, our approach to building this is so that we can build upon every experiment so that we eventually can get there. Okay, so that's the idea here. Yes?
When you see the error rate probably is 10 to minus 20, like what specific error correction code are you using? So for that 10 to minus 20, what specific error?
Yeah, so, and the way we're going to do this is with the surface code. And so I'm going to talk about a specific example of the surface code, which fortunately has the highest threshold that we know of, at least I know of. And it can go to the many orders of error correction to get this kind of thing. And although we're going to just talk mostly about how to correct errors, if you want to do logical gates, you just build that on top of the surface code. It's kind of automatically built in. It's forward compatible to that. Okay? So that's the reason I'm going to talk about the surface code. It's great. There's a wide variety of things. People are thinking about it. That's great. I'm going to give you one known direction on how to get there, which we think is pretty good. But, we'll have to see. But we're not trying to make it a little bit better. We're trying to go down a path to make it orders and orders and orders of magnitude better. Okay? And it's hard. You're starting with pretty high rates and you're trying to get to 10 to the minus 20. It's not obvious how you do that the high order. Okay, that's not obvious how you would do that. There's a lot of moving parts in this thing that gets there. Okay, so that's the motivation of what I'm going to talk about. And I think it's good. It's a very concrete, not too hard to understand example on how to get there. And it actually is compatible with what we're doing. And in fact, once I understood the surface code, that totally changed the direction of my group, and that got us to Google. That's pretty cool. Okay, let's go back to something you've already learned about, is that let's say you're in the ground state, but for some reason there's a small error in the block vector by epsilon. We need to correct that, okay? And what we can do is we can measure z with two outcomes with the probability of 1 minus epsilon squared that erases the error. And with probability epsilon squared, you see an x error. And this kind of basic idea is behind the whole concept of the quantization of errors, where instead of thinking that you can have continuous errors, you can say that you have a probabilistic error model where there's no error and a certain probability to get a bit flip or maybe a phase flip error. So I think you've been talking about that in some of the error correction, and that's the language we're going to use. It's been proved, people know that's the case. It's actually, to me, this really bold assumption that you can treat errors in this kind of probabilistic, simplistic way. And there are constraints on that, which I think we apply to, but this is one of the basic ideas we're going to use. So anyone have any questions on that? This assumption we're going to make? I think it's been talked about prior to this. Okay? And then we just need to know what the error rates we have to making bit flips and phase flips. Okay, let's talk about qubit errors. This is just a very general discussion. We have a classical error, classical bits. You can think of that as a coin on a table, or a coin on a table. And when the coin flips on the table, there's a force holding it on a table. There's dissipation. And because there's only the upstate and downstate of the coin, that's a very stable state. If you jiggle this a little bit up, because there's a restoring force and dissipation, the 0 and 1 states classically are very stable, intrinsically stable. However, in the quantum bits, in analogy, you have the block vector, which you can think of as a coin in space, where you have the amplitude and the phase. There's no preferred direction, no restoring force. Any small errors and rotation errors from any small force is going to give you an error. And thus, qubits intrinsically have errors. Okay, that's the analogy here that I'm trying to get across. So when you have a qubit state and you have an amplitude in the phase, if you have one qubit, let's say you want to measure the amplitude to see if it's screwing up in some way, you're going to randomize the phase, right? And then likewise, if you want to measure the phase, you're going to screw up the amplitude. It's, that's bad, okay? However, if you have two qubits, you can measure the amplitude and phase parity at the same time. Okay, here's the parity without the phase amplitude screwing up the phase parity and vice versa. And from doing parity measurements, you can stabilize the qubits. And then that's the basis of most error correction that people think about. So how does that work? Okay. I hope you've gone through this, but it's easy to go through it. This Heisenberg uncertainty, amplitude measurement screws up the phase, is due that the x and z and x don't commute. I flip the amplitude, and then I flip the phase. That's differently than flipping the phase and amplitude. So let's go through the math there. Flip the amplitude, 0 goes to 1 and vice versa. Flip the phase, you put a minus sign. Let's take the 0, 1 plus state, you do an x. 1 plus 0, you do a z, minus 1 plus 0. 0 plus 1, you do a flip a phase. 0 minus 1, you flip an x. 1 plus 0. This state does not equal this state. In fact, as you might remember from your quantum mechanics report, it's not that the commutation relation, it obeys the anti-commutation relation. By changing order, you actually just flip a sign. But of course it's not equal, so you have a problem there. Why is that important? Well, now what we're going to do is let's consider not 1 qubit, 2 qubits, and measure parities. A bit flip parity, x12 is x1, x2. Phase flip parity, z12 is z1, z2. Now, what about x12 and what do the parities do? So I write that out. I flip the x and z's, and each one of them gives me a minus sign. And because minus times minus equals plus 1, then these guys cancel out to 0, and you get a 0. So what happens when the parity amplitude and the parity phase commutes? What does that mean? It means these are classical-like variables, which means you can use the full apparatus of classical error correction to design your qubit error correction code. And all you have to do is go from a single qubit to a parity, and then everything looks like we have all our intuition for, and we have all these papers for. And that's what the majority of error correction algorithms are doing, is they're using this parity. Okay, does that make sense? Now, this parity operators commuting is very important. Okay, so we have the operators, they commute. What are the eigenstates corresponding to these parities? These, eigenvalues. You get these eigenvalues. What are the eigenstates corresponding to these parity operations, 2 qubits? Do you know what they're called? Bell states. This is why Bell states are so important to study and understand and use, because the parity of the Bell states have this classical-like relation to it, which you can then use to build interesting quantum circuits and do error correction and doing things. So this is what's going on with the Bell states. They have these kind of properties that are very important. Okay? This is stuff that's all in the literature. I may be talking about it in a different way. But this is key. So what happens? You have 2 qubits. Okay? And I measure the Z parity, and I get a plus 1. And then I measure the X parity, the minus 1. And because these 2 commutes, if I continue to measure the parities of these 2, it's going to be the same thing. Right? Because they commute. It's not going to change. And then, at some point here, I measure Z12, and it went from plus to minus. I say, there is a parity error. Okay? And I know there is an error. So I detected an error. That's really great. What's the problem? I don't know which qubit was an error. It's fundamentally hidden from you. Okay? So how do you deal with that? Well, what you do, and I'm just going to talk about bit flip parities for simplicity, and I'll talk how to build that up. You have 3 qubits. I'm measuring the parity between these 2. And here's the truth table, and here's the parity. Let's say it's 0, 0, 0. I measure the parities here. And let's say suddenly the parity changed to 1, 0. Okay? From 1, 0, I would say, well, 1, 0 corresponds to 1, 0, 0. And I'm going to say, hey, the first qubit flipped. And if I get 1, 1, decoding that, I'm going to say the middle qubit flipped. And if I decode the parity 0, 1, it's the right-hand one flipped. So I can decode. Okay? But what happens if between the 2 measurements, 2 of the bits flipped? like here and here, it's going to decode to 1, 0, which is the same as this. And of course, note this is the complement of this. So if I say, but of course if I see 1, 0, I'm going to decode it as this, because this is 2 qubits flipping, which is much less probability than 1 qubit flipping. So if I get any of these happened, I'm going to decode it as this because that's the most probable, but I'm going to make an error. Okay? So by doing this kind of continual coding scheme, I can uniquely decode for a single qubit error, which is good. But now I'm going to get an error in the decoding mechanism when I have 2 qubit errors. Okay? So what would you do to make it even be able to detect 2 qubit errors? You just make it longer. You have more physical qubits, more measurements. And then, you have a bigger truth table, and then you can figure it out. And then the idea is if you make this long enough, the chance of 10 qubits flipping in one operation is so tiny that you say you're going to be doing okay. And so you have to know what the flipping rate is and do all that, but you just make it big enough so that the probability of everything going wrong at the same time is low, and then you're okay. Okay? Yes?
How well can you make these parity measurements? Right? Because your qubit errors are like 3, 9,
Yeah.
right? But then when I was looking at your measurement slides, your measurement error was like 2 point something%.
Right. So I'll give you a physical example, and I'll talk about that. But basically what happens is, you have errors, and then you try to make it longer to do that, but then you're introducing more errors. And there's a concept of a threshold in which if your error rate is not better than the threshold, then you're generating so many errors and everything that you're just going to get screwed up and it's not getting better. But if your error rate's low enough, then the chance of all that happening is okay. But you have to, in fact, worry about whether the measurement is in the measurement or in the qubits, and you have to worry about all that, and you have to decode that. And I'll show you how to do that. There's a way to do that. But I'm just giving you the idea here of what's going on. This is the essential idea on how to do 10th order error correction, which you can easily see from here. But we have to talk about the detail of how it works next. Okay. So now we get into the surface code, which is the detail. Okay. So what the surface code has a long and nice history. I call this our paper in 2012. It's the surface code for mere mortals. This to me reads like a string theory. Very hard to understand. We tried to write a paper so that graduate students can understand. So 2012 paper, the details are all there. Hopefully you'll be able to slog through that. But the basic idea is this. What we have is a square array of qubits. The open one are the data qubits where they hold the states. And the dots here are the measurement qubits, are often called ancillas, but we like to call the measurement qubits as a little bit more clear. And then what you have is nearest neighbor connections between the qubits. Okay? So it's a 2D array, something we can build with an integrated circuit. That's what's kind of cool about this. And then what we're doing is we're running a cycle of gates through here according to whether it's a 4-bit parity, a bit parity, or a 4-phase parity, blue or yellow. So let's take, for example, this measurement qubit right here, which is measuring these 4 around it. And what happens in the qubit error correction cycle is we're starting off with the measurement qubit in the ground state, and then we do basically C-naughts around the 4 qubits around it, so that if this is in a 0 state, nothing happens, but if it's in a 1 state, this will flip this, and then since we're doing it multiple times, this is just measuring the parity. So if one of these flips, this will go to a 1. If 2 of these are in the 1 state, this will be a 0. 3 will be a 1. 4 will be a 0. So it's just a parity measurement. Okay, and then we just measure it here, which is equal to +1 or -1, depending on whether it's a ground or the minus state. And then we just repeat this over and over again. Okay? Those are the green ones. And then the orange ones are basically doing the same thing, only now this is flipped, and now we're doing a phase parity device. Okay? So now we're looking at the phase of these states, and the phase is plus. It's like being a 0 here, and if the phase is minus, or state is minus, it then gets flipped in the same way. So it's just a phase. We won't go through that, but just trust me, that's what's going on. So we're measuring bit parities, but instead of being 2 parities, it's on 4 states, either bit or phase. So measuring X or Z, or Z or X. Measuring Z, measuring X. And then those are going on the whole time. So you have these guys that are going around and measuring it at the same time. This is measuring it, and this is measuring it. And these two are interleaved in a way where they don't interfere with each other. So each time you have one of these vertical slices, like these are connected, and another slice, these are connected, and it's not interfering with each other. In fact, the order matters. But that's basically what's going on. And then every time you cycle through this Hadamard's and C-naughts and Hadamard's and measure, you're getting output of the state, and you're measuring the parity. So you're measuring the 4-bit, 4-qubit phase and bit parity over and over again in the way that I talked about. Okay? Everyone okay with that? So how does it work? Okay, you want to know how it works. Okay. The first thing to note about this construction is that these phase and bit parity operators commute. Okay? So it will take, of course, this one here commutes with this one because they're different qubits. Okay? But it's the nearest neighbors one that matter. And you see when you have this one here and this one here, and you do the commutation relationship, it's sharing 2 qubits. And we already showed that X1, X2 and Z1, Z2 commute. Okay? So the measurements of the bit and phase commute. And that means if we're running this surface code and there are no bit or phase errors at all, that means the measurement outcomes will be unchanging. It'll be some numbers of 0s and 1s, but it'll be unchanging. And we know there's no errors going on. And then when those values change in one cycle, you know that there is an error. Okay, in the same way I talked about before. So let me, with errors, you data qubits. So let's step through that. Let's say you're stepping through this, and in one moment in time, this was from a 1, 1, 1 and went to a -1, and at the same time this was -1, and this went to a +1. You had a change here and a change here. Okay? When this one changed, you said one of these qubits changed. And this one changed, you said one of these qubits changed. And it's very clear that you would decode that as there is an error here. Kind of just like in the way we talked about before. Okay? This changed, one of these 3, one of these 4, the error is there. Let's say you had a single qubit error, and the next cycle it changed again. So I can't write that. Okay, it changed again twice. Then we're going to say that was a measurement error because it changed and then changed back. That was something due to a measurement. So you can isolate when you have errors in space, that's a qubit error. When you have a error in time, that's a measurement error. So you can separate those out. Okay, that's the idea. Questions on that? Yes?
Sometimes you may not be able to distinguish between the measurement error and
Things can get complicated, but this is okay. And you can have errors due to that. But most of the time you can figure it out. They're well isolated errors. And of course what you're worried about is what happens when that, you get lots of errors, and then you start trying to match this up, and it's not clear, how to match it up. So if you have too many errors, then you're going to screw up. And then it's like what I talked about before. You have too many errors, it doesn't work. So it only works to some degree. And to match up these errors, you have to develop something called a minimum weight matching algorithm, which computer scientists have very good classical algorithms to do this. It's a little bit complicated, but you can do that. And in fact, those decoding algorithms are pretty efficient. I think they're order and efficient or something like that. They're efficient, so you can do that. But at some point, they won't work. And you have to work very hard to get that to work properly. Okay? So I'll talk about that, what happens here. That's definitely the problem. And I'll explain how that works a little bit more. Oh. So basically, D is the dimension of the system, and then lambda is how much below the fair error threshold you are. And basically, the decoding logic goes is factor how much below threshold you are, scaling with the size of the system. So if you scale the size of the system, you can decode the higher and higher order errors, and things get better. Okay, then I'll explain what all that means in a few minutes. Now, we can decode errors. You're saying, well, how is the logical qubits working here? Basically, you're encoding the state with a whole bunch of physical qubits. You have this grid here, and if you count the number of open squares, that's 41 data qubits. The closed squared are 40 measurement qubits. So you're extracting all the information out of the states, 40 qubits worth of information out of the 41 qubits. You're left with 1 qubit of information, and that's your logical qubit where you're holding the state. Okay? And this logical qubit, you can write logical operators for by writing this logical qubit as equal to x1, x2, x3, x4, x5, and the z state being these right here. And you can easily work out the commutation relationships so that XL, defined this way, is equal to minus ZL, XL, and that's trivial to see because you're always overlapping 1 qubit, and that has the anti-commutation relationship. It also turns out that these logical and ZLs commute with all the measures, the stabilizers, so that it acts as a separate degree of freedom. And okay, you have this, you're encoding your logical state very complicated way here. It doesn't tell you how to do it yet, use it, but you can see that that there is that piece of information left here. Okay, that's how it works. What I'm going to do is I'm going to talk about what does the threshold mean and how does this thing work with numerical experiments. Okay? So what we're doing is you simulate a surface code from size distance 3 by 3 all the way to 55 by 55, which you can do that. And what you do is you take these surface code things and you just simulate that with a quantum state, and then what you do is you say at every step to put in the errors there's a probability for you to get an error. So you add an error of x or y or z, or actually it's x or y or z on each of the states, and then when you have a C naught, there's all the possible combinations coming out of the C naught. So you put in randomly bit and phase flip errors for each of the steps of all the qubits in this. And then you run the surface code. Then what you do is you run the surface code and you get some final answer. And then you say, you have a decoding mechanism that says, okay, with the measurement outputs that I simulated, I have a decoding algorithm based on minimum weight algorithm, and you decode what the state should have been, and then you see if the state that you decoded was this actual state that you simulated. And that way you use a numerical Monte Carlo simulation to see how well the whole surface code algorithm works. Okay? So for example, at d equal 3, which is a small element, you see that if the error probability per step is around 1% or few percent, then the logical error rate for a bit flip is up here of a few percent. And then as this error probability goes down, then the output error rate from the decoding and doing everything goes down. Okay? And then you go to a larger surface code where this only corrects for single bit errors, and this will correct for 2 errors in one surface code cycle. You get the same thing here, but then it goes down steeper here. And as you make a bigger and bigger surface code so that you correct more and more errors, like I've been talking about, then the error goes down very rapidly. Okay? And this, in fact, defines the threshold of around 1%, whereas if your error rates are above 1%, making it larger and larger, in fact, makes it worse and worse. It just overwhelms your ability to decode, whereas if you're below the threshold, then making the surface code bigger and bigger makes it more accurate, more likely that you're going to correct the error, catch the errors and correct them properly. Okay? And you see, if you want to get a logical error rate 10 to the minus something big, then you want to be, let's say, a factor of 10 below the threshold, and you want to go to some high size of the surface code. So that's how you get to low error rates. Yes?
So, experimentally, is it better to use periodic boundary conditions or open boundary conditions?
I think it might be better to use periodic boundary conditions, but when you actually want to build and to interact logical qubits, that's not what you want to do, so it's kind of not an important thing. It was a surface code was originally called the toric code because of that, but you really need the edges for doing computation, so that's not so useful. Yes?
This does not include the measurement.
It includes everything. You have a probability of state generation, measurement here. And you can run models where you have a different error rate for the C naughts than you have this, and for measurement, and you can kind of budget, what are the important things. So it turns out that the 2 qubit errors are the most important, then single qubit errors, and then measurement. You're most tolerant to measurement errors. The threshold for measurement errors are 5% or 8%, and whereas the C naughts are like 1%. Mostly there's a lot more C naughts. So, okay, go ahead.
So here you're talking about one logical qubit. If you want to couple several.
I'll show how to do that in the end. Okay, but that's important. Okay, so that kind of tells you what the threshold is and what you want to do. I'm going to give you a very simple way to understand this. Okay, this is basically to understand these curves. You have to go back to high school statistics. Okay? So let's say we have, and this is basically what I talked about before. Let's say we have a chain of qubits, and we measure errors here, here, and here. The computed error is, you say these two, you said there was an error in this qubit, this guy, because there's not an error here, this is in here, and you decode it this way. But you can also decode this as the complement, where there's an error here, and error here. Both of these will decode to this. Which one do you choose? You choose the one with the lowest error, and this will decode properly. But if you happen to get this one, which is a higher order error, less probability, you're going to think it was this and you're going to screw up. You're going to get a complement error. Okay? So what's the probability of this happening? The logical probability is p squared. The logical probability is p cubed. Okay? There's 8 possible ways this can go wrong in all this. So 8p cubed, and then you just do the combinatorials of different ways that this can happen that can screw up. So get given this prefactor here. So here's a high school formula for estimating your logical probabilities. So for this thing, this simple statistical prediction of this data, again here, this predicts a threshold of 2% instead of 1%, but you see it basically predicts all the other lines. Okay? So kind of within a factor of 2, you can do it. Then you can fix this up some more and get it right. But that's all that's going on. Okay? It's that simple. Now note here that I'm assuming that the logical probabilities goes as p squared or p cubed. That means all these error probabilities are independent of each other. There's no correlation between them. And that is a fundamental assumption of all quantum error correction, of all error correction. If these errors are correlated, you're going to get messed up and it's not going to work. So that's something we have to test experimentally and build our systems to not generate correlated errors, so that each of these errors are as independent as possible. And we have to do measurements to do that. Okay? Now, given that you have these simple formulas and you know how it works, you can basically write a logical error rate fitting to that data. It's about 5%. This factor lambda is how much below the threshold we are. So that's about 1%. This is where the probability error is 1%. If it's 0.1%, we're on this point, and then lambda is 10 and 100. And this is the number of qubits that we have, and these lines, and this is the order of error correction, and these lines are what kind of logical probabilities. So if you want 10 to the minus 10 logical error rates, and you're about at a 1/10 the threshold, about 0.1%, that's a d equal 20, and that's about 1,000 logical physical qubits per logical qubit. Okay, so that's kind of how you estimate what's going on there. Okay? Good. There was a question about how you actually use the logical qubits. And this is in the paper. We have a full description of that. I'm not going to spend too much time here because it's a little bit too technical. But what you do is you take this big array, and then instead of making the logical qubits cross array, you make holes in the arrays. Let's say 2 holes. And then your logical z's goes around this hole, and your logical x's go around this hole. So you make a big array, you put holes in it, each pair of holes gives you a logical qubits. And then, this is the miracle of the surface code. If you want to do gate operations, for example, the C0, what you do is you take one of these, you have this being a pair of qubits and this being a pair of qubits, okay? And then what you do in this step from here to here is you take this hole and you start opening it up by stopping doing measurements, okay? And you can take this hole and open up a hole and then close it behind to essentially braid this hole around another hole and then coming back again, okay, by turning off and turning on interactions again. And that braiding operation gives you a C0. Okay, and I'm not going to go read the paper. It's you have to go through but you just take the surface code and start turning on and turning off things in the right way, and you can do logical operations. And the C0 is very simple braiding. The single gates have some also relatively straightforward ways to do that. Of course, the non-Clifford T gate is very complicated. You have to build a state distillation machine, and there's a big overhead for doing that, but everything else is straightforward in the surface code. So the thing is, you build the surface code, get that to work for logical, and then you just have to build it bigger and turn off and on interactions in the same way, and then you can build the logical qubits right on top of the hardware you've always been building to do the protected qubits. So it's upward compatible for doing computation. Okay, and not all ways to do error correction is so obvious that, you know, how you would do that. Okay. So let's talk about an experiment that we did to test this. So we have this big two-dimensional array. We eventually want to correct it to 15th order, being a 10th of threshold, then show operations. Okay, that's way far off. That's really hard to do. What we're going to do is take the surface code and just take a linear array of these things and only do bit flip correction, but do everything else in the repetitive way that you would do the surface code as a way to test the idea. So everything is getting tested in the right way, except we're only doing a 1D array instead of a 2D array. But we're trying to do the base experiment and do this right. So what we're going to do is the logical error rate is some small number, p over p threshold to the n. We're going to correct errors for actually n equal 1 and first and second order errors are going to get corrected here for 3 and 5 data qubits. And we're going to test for correlated errors and see if everything's going to work properly. Okay, so what we have here is a linear array of qubits. These blue qubits in here are going to be, no, the green qubits are the measure qubits. And then they're going to be C-naughted to the neighboring qubits to do the bit flip parity. So we're going to do the bit flip parity between the two neighboring qubits. We're going to do that and then get some answer and then repeat over and over again to do that. And then we're going to read out all the qubits at the end to see if we figured out what was going on properly. So this is just basically the surface code in one dimension, initialize, error detection, over and over again, measure, see if we're working properly. And what we want to do is we want to extend the lifetime and bring forth 1 and 2 qubit measurements. And the big thing is we're doing multiple measurement cycles. This is usable error correction. This is the way you would run a real quantum computer. Okay, that's what's nice about it. Measure it over and over again. Questions on this? So it's just a 1D surface code array measuring the bit flip parity. So this was the 9 qubit devices. These are the day qubits. These are the measurement qubits. These lengths are all a little bit different, so it's frequency multiplex. And then all our control lines are at the bottom. And this is what I said before. We start with, in the initial experiment, we're going to start with some entangled state, 0, 0, 0 plus 1, 1, 1. We're going to measure the parity here, see what happens. Error detection, do this over and over again and see if we can recover. And we're going to use the outcomes of these bit flip parity measurements to protect the environment giving us bit flip errors. So here is for 9 qubits. And these are the control waveforms for what we're going to do for 9. We're going to do 9. We have our C naughts, which are these pulses right here. And then we turn on our measure. And then we rate for the measure to decay. Maybe do a state flip if we need to symmetrize things. And then we do it over and over again. So we repeat in time, and we repeat over in the number of qubits. So the basic operations are pretty straightforward, but you have to do everything with all the qubits. And then at the end, we measure the qubits to see how it's working. Okay? There are lots of operations here. You really have to calibrate it well to get it to work. So here's the first check experiment we did. We started out with the 0 state, and then we did these operations here, which is pi over 2 operations, essentially a Hadamard, and then a C naughts, and then the swaps here. This basically gives us a G8Z state, 0, 0, 0 plus 1, 1, 1. So 0, 0, 0 plus 1, 1, 1. We can stop the operation right here and do quantum process tomography to see what state we get. And that's given here in this density matrix. We see states at 0, 0, 0 and 0 and 1, 1, 1. And we also see off-diagonal elements of the density matrix saying that we have good coherence between these two states. They're not, it's a quantum superposition. So you're creating that state nicely. Then what we do is we run 2 cycles of the repetition cycles, and we measure whether we had bit flip errors here. Okay? For the subset of events that we ran through, and then of course at the end here we do tomography again to get these results. For the subset of events where there were no bit flip errors here, so these were 0, 0, 0, 1, we measure right here that we get a G8Z state similar to this, a little bit less fidelity because it's taken some time, but not too much less fidelity. And it shows that the error correction, when there's no errors, you're still getting this complex quantum state. If, for example, on the particular algorithms on these 2 states here, we measured a change, so we had a bit flip. We have a bit flip here and a bit flip here. That says that the center bit here changed. Then when we do the correction, this is the density matrix we're getting. And then we said, okay, the center bit flip changed. We measured that. So you relabel these axes to correct for that. And now you get back to the original G8Z state. And note that the fidelity is lower compared to here, because although we can correct for bit flip, we can't correct for all the errors that are going out here. So the bit flip, when we do that, it corrects properly that we had a bit flip. I identified it properly, but we lose a decent amount of coherence because we're only protecting for bit flip and not bit flip and phase flip. So with this experiment, you can kind of see that the error correction cycle is working properly. Okay, questions on that? A more complicated experiment is for 9 qubits, okay, where we start with the 9 qubits. And then what we do over 8 cycles, we have the output of the measurements given here. This is an example. And then when we go through this, we measure the 5 data qubits in the end, and we got a 0, 0, a 1, 0, 0, so there's a bit flip here. And we have to look at the output of all these data to see, can that decode properly here. So there's this way to analyze this where what happened, you first extend this in some way, and then you detect the errors. And I won't go into that, but I'm going to say that these pairs of ones here are telling you that you detected a pair of error events here, a pair of error events here, and then some more error events here. This is when the output changed unexpectedly. And as you recall, what you have to do is match up the errors, because errors are all happening locally. So you build this graph of the detected errors, and then you decode by matching these errors. So this particular one here, these two matched, and this said that you had a bit flip error here. These two errors matched here, and that said you had a bit flip error here. These three errors, the most likely way to decode that is that these two had a bit flip error here, and these were two measurement errors, and you had an error here and an error here. And if you go down here, nothing happened to this qubit. You had two errors, so nothing happened. You had one X here, nothing here, one here. This said that the middle qubit was error, and that's what you measured. And that basically said that your decoding correctly affected your data, and you corrected it properly. So you have a computer do all this automatically for you for the 100,000 million events that you take, and then you can get a probability of error for the decoding mechanism. So here's the probability. If you don't do anything with the qubits, they decay down with the T1 state of about 30 microseconds. If you use 5 qubits, so that you're only can correct for single qubit errors, you get the blue line right here, which is better than this by about a factor of 3. And if you have a 9 qubits, so that you can correctly detect both single and 2 errors at the same time, you get an even lower decay of the state down to here. And you see, as you make the system bigger, it's getting better and better, so that you know that you're better than the threshold and everything's working right. And presumably all we would have to do is make the system bigger and bigger. This will get flatter and flatter, and you'll have your logical error rates go to 0. So we're better than threshold. Okay? And the degree that we're better than threshold is basically the ratio from here to here. 3.2 greater than 1, so better in memory for higher order. So that's the basic idea, and that's we have to make more orders. We have to do both bit flip and phase flip at the same time, and that's kind of where we need to go with these experiments in the next step. Questions here? So one of the interesting things is this, like lambda 3.2, it's the figure of merit for error correction. The logical error goes as this lambda to the minus m. Once you get lambda bigger than 1, then all you have to do is make it bigger and bigger, and it makes it better and better. 9 qubits is the simplest experiment to measure lambda, at least for bit flip. And then what we want to do is make a 2D array so we can do bit flip and phase flip, do everything properly, and measure lambda for the full quantum system. That's the next thing to do. One of the things you might want to ask is this lambda x of 3.2 makes sense. It's predicted to be about 0.03 divided by p, which is the error per step. Because it's bit flip, the threshold is 3% instead of 1%. Basically, the measure errors are averaging of about 1%, so 0.01 average p is reasonable, consistent with lambda x. Okay. So numbers make sense, at least within a factor of 2. The last thing I wanted to show here was the idea, are these errors correlated? Remember, the only way we're going to get 10th order error correction working if all these errors are uncorrelated from each other. If they're correlated, then it's not going to work properly. So this is the raw data out of the experiment. This is the probability. Let's say you started with 0, 0, 0, and you were flipping things to pseudoly randomize it, but you ended with 0, 0, 0. There's a certain probability of getting 0, 0, 0 at the end. These are all the cases for 1 qubit error. These are all the cases where there are 2 qubit errors. Here are all the cases: 3 qubit errors, 4, and 5. Okay? You see that the probability to get more and more errors goes down with the number of errors. And in fact, you can compute the means of all of these, which are given here, and it's going down nicely exponentially over here. And there's no obvious correlation up to 5th order error correction, to some error bars of the data there. So there's not obviously anything horribly going wrong here. But, clearly this has to be tested. So this is kind of an example. We're looking at this data, how you should be able to, check at least approximately whether things are having a problem with error correction. Okay? That's all I had for today. Any questions before we close out here? Yes?
So, what's the main challenge when you build the 2D structure similar to this one?
What is the
main difficulty?
So building the 2D structure is what we've been working on at 4 years for Google. So we did this, and then right at this time we moved to Google, and we've been basically building up the capabilities to do that, to build 2D. And it's taken us 4 years. So it's a lot of work just to get all the engineering right. So as you can see from the 1D structure, you bring in the wires just from the side. When you build a 2D structure, you have to bring the wires in from a 3rd dimension and build a chip to do that. And also to get all the qubits to tile together well, you have to compactify the resonator readout near the qubit so that you can tile the resonators as well with the qubits. And then you have to wire that up and then build structures so that you don't get a lot of crosstalk from all of that. So there's a lot of chip design and engineering going into doing all that. And, it's taken us 4 years to, figure out how to do that. And, there's a lot of testing going on in the meantime to make sure that as we move to the new structure, nothing screws up. Another big thing is when you're measuring 5 or 10 qubits, you can have a couple people there kind of manually tuning things up and getting it to work. By the time you get to 50 qubits, 72 qubits, you can't do that anymore. You just drive yourself insane. So all the knowledge of many students and how to tune up whatever has to go into a software algorithm so that can be automatically tuned up and calibrated. And that's a lot of software effort. So those are the kind of things that we've had to do. So things are working. We're getting it all together. We're starting to run these experiments. We hope, this year we'll be able to, show how these systems are working. It's essentially built on this, but there's a lot of, more design you have to do. And, it's kind of a competitive landscape with other companies and the like. I'll show some pictures of what we're doing, but the details of which will be forthcoming once we publish the paper. Okay, there's a lot of stuff going on to get this to work right. Yes?
So it seems to run some useful algorithms like quantum chemistry, you may still need like 200 logic qubits, which might mean a billion physical qubits. So
Yeah.
what's the strategy to proceed?
Yeah, so especially the Google theory group has been thinking about quantum chemistry. I'll show a table hopefully tomorrow on this. But yeah, you're going to need maybe roughly 1 million physical qubits to do that. Right now, we think we can just take this design and kind of brute force scale it up to, certainly 72, but maybe up to 1,000 or a few thousand like that. And there's a lot to test at that level, for the error correction and whether it's working right. So we have our work cut out to do that and maybe do some other algorithms. But to go to the million, we'll have to somehow put the control electronics cold to be able to connect all those wires. And although we have general ideas how to do that with cold CMOS or Josephson junction logic or something, I'll be honest and say we really don't now know how to do that yet. And that's something we're going to work on in the next 5 to 10 years to figure out how to do that. our philosophy is a little bit, we need to get experiments like this working right, because unless you get your error rates down to 0.1% and can build complicated circuits, thinking beyond 1,000 is just, just fantasy. So we have to be, grounded in real experimental world to figure out how to do these things. How do we actually put this together? And then we have to figure out how to build it. So, but that's hard. We don't know how to do that yet. But we think we can do a lot to 1,000 or so, at least 100 or 1,000. That's a really interesting level. Thank you. Okay, that's it. Thank you very much.